Okay, in this video we are going to look at how currents work in a three-phase delta system. In a delta system, if I have a delta connected load supplied from a delta connected generator, that load will draw a certain current from the generator. The generator supplies the voltage to the load, and the load will draw current from the generator. And if we look at what the load draws in line A, we see that when line A comes to this point on my load, the current is then split and goes to the resistor in phase A to B and the resistor in phase A to C. So you will see that in order to find out what line current A is, line current A will be split when it gets to the load into the A and B phase and the A and C phase. The same thing is happening, of course, at the generator. Two windings of the generator are supplying that line current for the load. We're more interested in really what happens once the current gets to the load. And so for line A, the current splits between A to B and A to C. For line B, the current drawn by the load through line B at point B splits and goes through phase B to A and phase B to C. So the load will draw current through line B that is shared from the phase loads B to A and the phase load B to C. Again, the same thing for line C. As the load draws current through line C, when it gets to point C on the load, it splits between phase C to B and phase C to A. So there's a difference in currents in a delta connected load. We have line currents and we have phase currents, and they are different values. If I look at a delta connected load and I want to see exactly how phase current and line current works in a delta connected load, we'll look at a balanced load. And to have a balanced load, of course, we have to have two things always for a balanced load: the same impedance or current in each phase and the same power factor in each phase. That's what we have here. And because it's a resistive load, the voltage across the load and the current through the load for each phase are happening at the same time. To draw this on a phasor diagram, we would start with the voltages. In delta, there are only three: phase or line voltage A to B at 0 degrees, phase or line voltage B to C at 240 degrees, phase or line voltage C to A at 120 degrees. And the load that we're using is a purely resistive load, so the currents are in phase with the phase voltages. The resistor connected in phase A to B draws a current of 10 amps, so that IAB, that phase current, is right in phase with the phase voltage A to B. The load connected in phase B to C that draws 10 amps is right in phase with the phase voltage B to C. And the resistor connected in phase C to A that draws 10 amps, that 10 amps through that resistor in phase C to A is right in phase with the voltage across that resistor in phase C to A, because they're purely resistive loads, and voltage and current are in phase. To calculate line currents, we'll start with line current A. We know that line current A is split up between phase A to B and phase A to C. So we have to add those two phase currents on our phasor diagram to find what the line current is drawn by those two phases. Here are the phase currents on my phasor diagram. If I want to find line current A, it's made up of phase current A to B, this phase current. So phase current A to C is exactly the opposite location from phase current C to A, and is located, if C to A is at 120 degrees, 120 plus 180 gives me phase current AC at 300 degrees. So the two phase currents I add up are A to B at 0 degrees and A to C at 300 degrees. And then we just simply put together our horizontal vertical table to figure out at the 10 amps for phase A to B at 0 degrees, how much is horizontal, how much is vertical. 10 amps times cos 0 degrees will tell me what the horizontal part is. 10 amps times sine of 0 degrees will tell me what the vertical part of it is. The same thing for phase current A to C. 10 amps times cosine of 300 degrees will tell me what the horizontal part is. 10 amps times the sine of 300 degrees will tell me what the vertical part is. And again, we just add those values up to get the total horizontal, total vertical. And we use Pythagoras' theorem to find the line current. So it is the vector sum of 15 squared, or the square root of 15 squared plus 8.66 squared. 17.32 amps is the line current A, and the line current will be 30 degrees away from the phase current on our phasor diagram. And we also know that if we have a balanced load, that the line current will always be root 3 higher than the phase current. So we do not always have to do this math if we know that it's a balanced load. Once we know the phase current, we just multiply the phase current by root 3 to find the line current. To find the line current in line B, that line current, when it gets to the load, is split between phase B to A and phase B to C. So we need to know where those two phase currents are on our phasor diagram in order to figure out the line current. We're going to show on our phasor diagram what we already calculated for line current A. That line current A is the vector sum of A to B and A to C, and is located directly in the middle between the two, and is 30 degrees away from phase A to B. The line current is 30 degrees away from the line voltage. To find line current B, we know that it is phase current B to C plus phase current B to A. Phase current B to C is located right here at 240 degrees. Phase current B to A will be the inverse of this phase current we have at 0 degrees. So phase current B to A will be 180 degrees away at 180 degrees. Line current B is made up of phase current B to C and B to A. So in order to figure out our line current, we have to break each phase current into horizontal and vertical. If we take 10 amps at 240 degrees, break it into horizontal and vertical value, and take 10 amps at 180 degrees and break it into a horizontal and vertical value, we'll get totals, again, that will make up the total horizontal value and the total vertical value for our line current B. And we would use Pythagoras' theorem, the square root of 15 squared plus 8.66 squared. At this point, it doesn't matter whether the values are negative or positive, because as soon as you square them, they give you a positive number anyway, and it just gives us the value of that current. And again, the line current B ends up being 17.32 amps, and again will be 30 degrees away from our phase current. And again, rule 2 for delta is that line current equals phase current times root 3. The 10 amps that was our phase current times square root of 3 will give us 17.32 amps. So for balanced loads, we will not need to do this calculation. We can just take the phase current, multiply it by root 3 to get the line current. And we know that that line current will be 30 degrees away from our phase. And if we know the phase current, or if we need to know, if we have the line current and we need to know the phase current, we just take the line current divided by root 3 to get our phase current. The phase current is always a smaller value than the line current. To find line current C, Again, we know that the current coming down line C, when it gets to the load, will split and go between load C to A and load C to B. In order to find out that line current, we need to find where the two phase currents are on our phasor diagram and then vectorially add them to get our total line current. So again, we're showing on this phasor diagram line current B ended up 30 degrees away from the phase current, ended up 30 degrees away from the phase current and voltage we have for phase B. To find line current C, again, we need to find where phase current C to A and C to B are. C to A is right on phase C to A, the load connected there. C to B will be the opposite of phase B to C current. If it's labeled opposite, that current will be in the opposite direction. So phase C to B current is 180 degrees away from 240, which puts it at 60 degrees. And again, the line current will be the vector sum of IC to A and IC to B, and will in the end become right in the middle between them because it is a balanced load. We could find that line current fairly easily by taking the phase current times √3, and I would have 17.32 amps located right at 90 degrees. We can use the math to prove it. If I take phase current C to A and break it into its horizontal and vertical part, take phase current C to B, break it into its horizontal and vertical part, the totals again that I get will give me a triangle which has actually a horizontal of a total of 0 and the vertical of a total of 17.32. So this really isn't a triangle. It's really straight, just a vertical line. I can still use Pythagoras' theorem to figure out what line current C would be. It's the horizontal value squared plus the vertical value squared. There is no horizontal value. The vertical value squared, and then take the square root of it, gives me 17.32 amps. Again, that's the line current. And again, that line current will be 30 degrees away from the phase current. So for balanced loads only, the line current will equal the phase current times √3. Or the phase current equals line current divided by √3. And on this phasor diagram now, we have all the important voltages and currents plotted. And for balanced load, again, these calculations are fairly easy. It's fairly easy to figure out what your line current is and to know that it's always 30 degrees behind the phase voltage. In an unbalanced load, the calculation is a little bit different. We'll look at that next. And another thing to remember as well is that in balanced delta circuits, the line current will lag the phase current by 30 degrees. Our line current will always be 30 degrees behind our phase current.